So thank you everyone for coming. My name is John Fultz. I'm the director of user interface development at Wolfram Research, and what I'm talking about today has nothing to do with that. I'm talking about integrating Git with the Wolfram language. This is kind of a pet project that I began sometime last summer or early fall, and has turned into some really interesting technology that we've been using internally. We're not shipping it yet, but I'll talk more about that in a little bit. If you don't know anything at all about Git, I'm afraid that my talk will probably not be very enlightening to you. I welcome you to stick around anyway, but I have a half hour and I have a lot of material to cover, and bringing people up to speed in Git can't be done under a half hour, even under the most ambitious of circumstances. And also, I'm going to not take any questions until the end. Hopefully I can get through and we'll have time for questions, but I really want to try to get through a lot of material here. But somebody yell at me if the screen goes out or something like that. Okay, so I will give a very brief introduction. What is Git? But this is a 60-second introduction that probably will still leave you lost if you didn't know what it was before. First and foremost, Git is a version control system. If you're familiar with CVS or Subversion or Perforce, that's what Git is. That's its purpose in life. It's decentralized, and this is very different from a lot of the older systems like CVS and Subversion. What it means to be decentralized is there is no central server that you have to deal with. I mean, you may have a convention of people using a central server, but all the information you need about the repository lives on your system. And when you're making commits to your system. You don't need wires or Wi-Fi's or anything of the sorts. Git represents commits, not just commits, but also directories and files relationally to one another in a directed acyclic graph. And each of these things, commits, directories, and files, they're basically objects, and they live in an object store. And when you look in a Git repository, if you have a repository on your system and you look in the hidden directory, the .git directory, most of what you'll see in there is these objects, which are kind of anonymous because they're indexed by hexadecimal hashes, which are SHAs, and people in the Git world refer to them as SHAs quite often. So if you want to identify a commit uniquely, you can identify it by its SHA. So that's the basic introduction of what we're dealing with. Oh, and I say here, commits, trees, and blobs. A blob is just the object store version of a file. But it's stored without a file name. The file name is in the thing that indexes it. Okay, so just a little bit of a visualization here. So I have a very simple repository here, and I can't keep it this magnified for the entire talk, but I can do it for this slide. Here is a simple repository that has 3 commits in it. Now, the first commit is actually the one on the right here, which is the commit that has no parent. And you can see this commit has metadata attached to it. We know that it's an object. It's an object of type commit. It points to a tree. And a tree is basically what we think of as the stuff that we put into version control. It's a directory that will contain files or other directories. It has information about when the commit was made, by whom. It has the SHA, of course, and then the commit log. And there's some other metadata in there too, but that's the principal bits. Now we can actually kind of dive a little deeper in here. I'm using the graph functionality, which kind of relayed this out a bit. Oh, and I should have said, so that was the first one. But then this second commit here, this has a new piece of metadata. It's a parent that points to the first commit. And so I'm representing that as a graph here. And so these green blobs here, or these green rectangles, I should say, are commits. And each one of the commits points to a tree, and so I've exploded, and you can see the tree here. And so in this case, a tree is, for this particular commit, is something that contains a single file, just readme.txt. And then I make a change here. In this one, I added a second file. And this third one also has two files, but one of the blobs is different. I made a change to one of the blobs. And I won't belabor the point too much, but you can see here the relationship. So this blob is actually being used by two of the root trees there, as is this one. And this one is unique to the final tree down below. So that is the basic idea. So why access Git from the Wolfram language? Well, Wolfram language, we like to call it a symbolic language. What does it mean to be a symbolic language? It means that data and code are totally the same. And you want to treat your data like it's code. You want to treat your code like it's data. That's fine. And one of the things that we built on that is thinking of our tooling as being fully accessible from the language as well. And this is the one place where I can play the part of the front end person because that's what the front end is. The front end could have been just a stupid editor that does maybe some very impressive stuff, but is not accessible from your code. But in fact, it's fully accessible. And a lesson we learned that this is really useful. So being able to access your tools from your code is a known good. In terms of version control, we're looking at Git because Git is basically the unchallenged leader. There are lots of people who have various problems with Git, in terms of usability or whatever, but very few people would argue that today and for the foreseeable future, in terms of mind share, Git is definitely the leader. And something that's been missing in version control for a long time is the ability to support merging of notebooks. Notebooks are structured documents, and version control, uses kind of standard diffing sorts of algorithms which look at things by lines. We're not structured by lines. We're structured by expressions. So having integration so that we can actually achieve a respectable merging of notebooks is important. And it turned out actually that we as a company made the switch to Git over the course of the last year, and it turned out that having this set of tools available to us was really valuable for our internal tooling, and I'll go into a few details of that a bit later. So basic introduction. And this is, it's just an addition to the language. It's, and in most cases, I try to keep things fairly close to the command line, so you'll recognize things pretty quickly. There are a few places where I make a few differences, but I don't think they're worth dwelling on too much. So how do you get to a repository? So you can open a repository, and when you do that, you get a typeset thing. Behind that typeset thing is just a rich association that describes the object that it was pointing to. You can also clone something, and I'm doing a local clone simply because I didn't want to potentially have network problems here, but everything works fine on the network too. with certain modes of authentication. Or you can just create a new repository completely from scratch. And here it created a directory that didn't exist before. And so I'm gonna use this rnew for the new repository for a bit here to just show a few things. So what can you do with a repository once you have it? Well, you can get its properties. And so here are what the typical properties of a new repository looks like, depending on how you create it. It might be a little different, but that's the basic idea. So and we can see here it is empty. That's the most important thing right now. We can also take a look at its status, and there's not much interesting in status at the moment, but I'll come back to that in a second. So let's put a file in that directory. Okay. So I'm just taking rnew and kind of an association type fashion. I'm just passing the working directory to it to get that. And so I just put a file in, trivial file. But now if we run git status, now we see that that we have something sitting in there. Okay. So Git has a system which takes a little getting used to, where unlike many other version control systems, you don't just commit everything that's in the repository, or everything that's in the working directory. You have to add, and it's not really adding new files, it's adding changes. So you made a change, you need to add that change to get it ready to go into your commits. So and that goes into a place called the index. So we run git add, and we do git status again, and we see that it's moved from the new area to the index new area. And now we can do a commit. The commit includes a log message here, and it produces a nice little object for us. And we can get our properties on that. And we see this is very much the same sort of thing we saw in that earlier slide with the dataset tooltip that I popped up. And in this case, we see a timestamp that matches with about 10 seconds ago. And at this point now, if we go back to git status, we will see that the git status is now back to empty again. Because status is looking at the changes relative to whatever your head commit is. And we do have a head commit. We didn't have one before, but we sure do now. And now it's telling us that head is pointing to the master branch, which is master is kind of the default branch that Git uses. So I also have a notion of git close. It's not necessary to use git close, but sometimes the library that we're using for accessing Git, it sometimes will lock down some resources, which if you want to like delete the directory or something like that, it's may be impossible to do. So git close is an optional thing, but something that you can do. Okay, so some more advanced concepts. You can access arbitrary revisions. Okay, so here I'm now not referring to the new repository I created, but I'm referring to another repository I opened, which in fact is the repository that I've been developing Git link in. So we're actually looking at some statistics, some commits and such from the object that includes this code. It's very meta. So here we go. I'm just saying, give me the commit which represents the master branch in that repository. I can also say, give me a range of commits. Well, so once again, I'm saying master, when what it understands is, oh, range of commits. You mean everything all the way back to the beginning of time. As long as there is a parent-child relationship going back from master, it will be uncovered here. So you might want to do something a little more flexible, where you want to kind of mix and match ranges. And so here's something that's very common in Git, is the ability to say this branch but not that branch, which is to say that I want all of the, starting from this branch, I want it and all of its ancestors, but then strike out all of the ancestors of this other branch. So in this case, I'm looking at a branch that I have, standard notebook merge, and I want to find everything that's on that branch but is not on master. So things which are unique to that branch relative to master. And in this case, it's 4 commits. And indeed, if I graph those commits, and the branch was called standard notebook merge, and we take a look and we see, yeah, this is a commit from Lou D'Andrea, and it kind of looks like it's implementing standard notebook merge. So did the right thing. Okay. Some more advanced concepts. You can access trees and blobs directly. And you can do this from the Git command line. Most people don't, but actually I've discovered since adding this functionality that it's become very natural in some cases for me to do this in the Wolfram language. So in this case, I'm just accessing the root tree for the master branch in the Git link repository, which doesn't look very big. It doesn't look very big because it points to a bunch of other trees. So each one of these trees is a subdirectory. If I just take that, the second guy there, which is a blob, and then I can just read that, and it just brings it back to me as text. And Git read blob can actually not just read text, but it has import running behind it. So you can pass it any import format that you want. You could have it reading and displaying PNGs, for example. Okay. So with that as kind of a background, let's do a little coding here, and let's try to do something practical, a nice small problem, but one that would be kind of difficult, and trying to do from some other language or from the command line or something like that. Let's find some line counts of what we have in the repository. So first, we're going to start with getting the object that we want. And so there's our commit object. That object, we need to get the tree that it points to. And so there's a tree. And then what we really want to do is we want to get everything inside that tree. So we can do git expand tree. It takes a second argument, which is kind of a level spec. And so we'll give it an infinite level spec, and that will actually then give us, expand all the subtrees into files. So everything down here now is a blob. Okay, and we don't want all the blobs. I could line count the entire repository. That's not useful. I want to line count. Let's line count the C++ code. So we'll select that, and we will do, we'll look for a string match queue, and string match queue of, so we have the name field in the association, so we're matching name against, and we'll have to choose a pattern here, and let's say a string pattern of something that ends in either .cpp or .h. Okay. And there we go. And let's see if we get something a little more reasonable here. Well, that's given us something different. And yeah, it looks like this is C++ files, or CPP and .h files. Okay, so let's get us down to we just want the list of blobs from that. Okay, and there we go. There's our list of blobs, which represents in the master branch every file ending in CPP or .h. Okay, so that's good. I put that code basically here. So this much. And then it built a little function out of it. So a get line count function, which does this if it gets an object that looks like a commit. And then it calls itself recursively. And then when it gets an object that is a blob, it It basically just does something very simple. It probably could be done more efficiently, but get read blob, string split it, length. Okay, so let's do that. And line count, and there we go. That's about right. That seems plausible. Okay, good. So let's do a time series. So I'm actually running a time series over the entire set of commits, all 272, I think, of them it was. And this takes just a little bit to run, but should be coming out any time now. And we'll go ahead and do the dateless plot of that as well. And so this is very straightforward code. I mean, we wrote half of it while I was standing right here, and this is taking longer than I expected. This wasn't taking. There we go. There we go. Okay. And so I'm going to have to skip a little bit here for lack of time. There is this artifact here, which was due to the fact that the data is not clean because there was some extra code that had gotten copied in at an early stage, and I have some slides here that talk about how to find the this is I can run this comparatively quickly. So what I'm doing here is I'm just looking for anything that's over 6,000. Let's just look for anything over 6,000, the entire history, and let's just see what commit objects those were. And then we'll take a look at one of them, and we'll see what the outlier was, why the data seemed so odd right there. And when we do that, we'll find that we look here, oh yeah, that's right, because at some point, for convenience sake, I had copied mathlink.hn. And that's kind of throwing the data off. So, and I'd also copied in Wolfram library.h as well. So I'm not going to run this right now, but you can see it's kind of very simple. We can just rerun the original thing with just removing the line counts for mathlink.h and for Wolfram library.h, and there we go. And this is this whole process running through this took me about 20 minutes. So very easy to do, and I have a couple other fun little examples here, which I'll show you very quickly because I am running low on time. So this is in 13 lines. I built a browser that allows you to look at files and open them up or whatever, and choose whatever branch you want to look at. And then that was too easy. So then I built a browser which allowed you to take two branches and then see what the differences were. So here's a case where the differences are in orange. So inside the git link directory there's a difference. Inside there's difference inside both documentation and kernel, and you can take it all the way down, and then if you end up with a notebook at the end, you can even open it up and using the notebook diff tools. So okay, but this is kind of fun, but it solved real problems for us. When we migrated from CVS, it was a hard, difficult task, and it was the tools that we had didn't go all the way for us. Required some significant post-processing. I wrote it all in the Wolfram language. We also find ourselves kind of routinely doing, having kind of scriptability needs. One of the examples is, we use a pull request model, so there are a lot of named branches flying around. They don't always get cleaned up, so having a way to automatically find feature branches which have been merged and clean them up. We implemented a really interesting tool which also helps us to automate dealing with multiple repositories. Google did this twice. They did it with Android, and apparently they failed so badly they did it again with Chromium. And we did it once, and we're happy with it. So go Google. And also, we created a very interesting way of doing deployment of development branches into nightly builds, which I won't go into the details, but basically allows us to be to keep our master branch clean. This is part of what has allowed us to ship new features every 2.5 months for the last 6 months. Okay, and yeah, we built a thing. It's very impressive. It works, it's a nice interface, and 50+ developers are using it every day. So we are eating our own dog food here. When you get it, it will be heavily tested. So three-way notebook merging, I wanted to show this real quick. So this is, okay, so we have our notebook here. So if this is the base version of it, and then the version which is on master, the version which is on our feature branch, and then merging. Despite the fact that there were changes all over the place, merging, not that much of a, except it didn't update, did it? Ah, look at that. It didn't update for some reason. Okay. Ah, there we go. Sorry, was evaluating the wrong thing. There we go. So yeah, and so there we have our three-way merge. Been waiting for this for, 15, 20 years. Okay, so when's the shipping? Large amount is already done. Mostly it's about getting the functionality that, we have the functionality that we really needed, but mostly it's about trying to cover more, enough Git functionality for it to make sense for people to say, yeah, now I can do everything I need to do in Git with it. Some of the details I've talked about might change before we ship. I'll update this talk to reflect any changes. What do you mean update? Where are you going to find it? Oh yeah, we have a GitHub presence. This talk is on GitHub. Not difficult to remember, github.com, and then after that, Wolfram Research. So this talk is repo number 1 in the Wolfram Research organization. More to come.